Freedom is slavery.
Okay, on your first word, Mr. Oya. Or Ms. Oya, 2 + 2 equals 5.
All right, let's do this problem.
Started.
Okay, I mean, I've timed it to start, so everybody's got phones and stuff away.
Put down.
Peter.
There we go. Okay, so this one, what I want to do is, you could probably almost do these problems now, but chapter 11 just gives us just a little bit extra. So then, not much.
Is this being recorded?
This is being recorded. It's actually recording.
You
Yes.
say that and then it's not.
No, this is definitely being recorded. I can see the little thing blinking. Okay, so how about this? We got this car, 1,049 kilogram car, slows from 51 meters per second to 40 meters per second by applying constant braking force, right? So uniform acceleration of 1,699 newtons. The car then travels at a constant speed of 40 meters per second for a while. Later, the car slows from 40 meters per second to 29 meters per second by applying the same constant braking force. The ratio of the distance covered during the first deceleration to the distance covered during the second deceleration is what? So how are we going to do this?
So
You have
gotta
to split
do
it
what we
into
first
two
did.
separate ones.
Okay, we got two separate ones, so let's do that. So we got part one, which is the first deceleration. Okay, how can we relate this information to a distance without having to do any kinematics or anything like that? Can we just use work and energy stuff?
So we have the force and velocity.
Mm-hmm.
Oh, yeah,
Find out how long it takes us
So
to stop.
are we trying to find power at all?
We don't need any power.
Okay, so we don't need that.
We don't need that, but
So all we need to do is figure out the work, so then we can figure out the force. We already have the force, so then that would give us the distance.
So the change in velocity is 11 meters per second.
okay, so we know that the velocity's changing, right?
Oh, I figured it out.
How many
No,
forces? You got an idea?
What we need to do is we need to take the 1/2 mass times velocity squared equals the KE, and then figure out the change in KE to figure out the work net. We have the work net, then we can equal that force times the distance, which we can use to find the distance.
Okay, we're on the right track. So let's start off here by saying, so we know the work energy theorem, as we've already talked about it, says that the net work
It'd just be the change in
equals the
velocity.
change in kinetic energy, right?
Find the change in kinetic energy.
So we just have to find
Values.
all the forces that do work and add those up, and that's gonna equal the change in kinetic energy. So this is on a level ground, right? How many forces are doing work on the car?
Friction.
Okay, name them. Okay, normal force and gravity do zero work. How come?
Because it's this one.
Because they're acting vertically and the motion is horizontally, right? So they don't do any work.
What about
Work was
friction?
only vertical.
Okay, friction.
And it's only in the direction of motion.
And the tires.
Okay, so the tires, it's when they put on the brakes though, right? And they're decelerating, the car's not being pushed down the road. The friction is slowing it down, right?
Yeah.
Does that make sense? So the only three forces acting are friction's acting horizontally, normal force and gravity and weight are acting vertically, right? Of those three, the only one doing any work is going to be friction, right? Everybody agree?
Yeah.
Okay, so then the work due to friction is equal to the change in kinetic energy, right? That's the only force doing work. So what's our formula for calculating work due to a force? Force times distance, okay. So the frictional force, let's just call that script F, times D, which is the distance it travels through, right, must equal the change in kinetic energy, right?
Yeah.
So that would just be KE final minus, I'll just call it this, KE initial, right, KE nut. Okay, well, we know what the frictional force is. It's that, right? Agreed?
Yeah.
We know what the initial and final speeds are, and we know what the mass of the car is. So we got everything we need, right? So the only thing we're missing is D, right? So if I solve for D, D just equals, let's turn that into 1/2 m V final squared minus 1/2 m V naught squared, right, there's my change in kinetic energy, divided by F, right? And that's just calculator stuff, so we can plug all that in, and what do we get?
So would V final be 29?
No, V final is, we're doing the first part up here.
So it'd be, the V final would be 40.
V final would be 40, V initial would be 51, right, because it's slowing down. Now, could we just say, like, the change in speed is 11 and say 1/2 m times 11 squared? Negative 11?
Yeah.
Mm-mm.
No.
We can't.
Huh.
We can't, because the difference between 51 and 40, the square of 51 and the square of 40 is a lot different than the difference between the square of 40 and the square of 29. Right, exactly. Yeah, it's not a linear relationship. I mean, think about like 4 squared minus 1 squared. They're 3 apart, right? 4 minus 1 is 3. 16 minus 1 is 15, but now if I go 7 squared minus 4 squared, that's a lot bigger number, right? See what I'm saying? So we'd have to then, okay, so we're going to have to just redo this expression, but we can just kind of cut and paste. So we're going to get on top. I'll make this, River, I'll make this a fraction for you. How's that? So on the top we get 0.5 times 1049, okay? And if I really wanted to, I could have factored out a 1/2 m on the top, but we don't have to. Times 51 squared minus,
Wait, isn't V final 40?
what's that?
Isn't that
Can I cut? No, I can't cut and paste. No, oh, you're right. You're right. Thank you. Just seeing if anybody's paying attention.
I got you.
But either way,
So,
I guess.
wouldn't you wanna stick all that in parentheses, or I guess if it's already
No,
that
don't
way,
need to.
so.
It all adds up.
What was that?
So my house is
51 squared.
That should get, save that.
Divided by, what was our force? 1699. Everything's standard units, right? So there's the distance that they covered during the first deceleration, right?
Yeah.
Do we agree?
413 kilometers?
So
Or
then
just
for the
meters?
second part, would you
Yeah,
just put in the
kilometers.
different velocities?
Yep.
Oh,
Yep.
that's easy.
Yeah, so for the second part, it's the same calculation, isn't it? The only difference is
Oh,
now
I take that.
my initial and final velocities are different, right?
Yeah.
Okay. So the final velocity should be, or initial velocity is 40.
Yeah.
What was that, F?
Oh, what did I just do?
Is that F
Yeah,
on
just
the
put
bottom
multiplication,
times?
multiplication, 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 multiplication.
Right there.
F on the bottom of the equation.
Then I gotta delete
Yeah, look at that.
that.
Can you guys read those the numbers?
So can you not?
No, not even close.
Is it because you're blind?
They're on the contents.
Oh, yeah, that's fair.
Okay, there's the distance for the second one.
So you just take the difference of them?
Just taking the ratio of the, was it first over the second?
I don't know.
Probably, yes.
Ratio of this, yeah, first over second, right? So the ratio is, so the first time we're covering,
It would be
Hey, isn't that what I said it is?
roughly 2 times as much distance when you're slowing down the first time.
Wait, so when you put it in the Moodle,
Mhm.
would you do like 410, like, how would you put that in? Would you put the 1 point something?
So you would just put, they just want it as the ratio of the distance covered. So I mean, you could just put a decimal if you want to, just rounded to 2 places.
So it'd be
Right.
2.0?
So it'd be 2.0, yeah. Make sense?
They wouldn't want the actual ratio.
Uh,
Like actually calculated.
No, the ratio, just meaning a number's fine. What am I doing, moving it somewhere?
Yeah,
There we go.
perfect.
Yeah.
So I can just get it to the
Are you recording this?
Yes.
Recording. So once again, there's yet another argument to support the idea that you shouldn't drive too fast because look at the difference it makes, right? You cover a lot more ground while you're decelerating than you do when you're going slower, right?
How many miles an hour is 51 meters per second?
It's pretty fast, 51 meters per second.
It's
That's
not
gonna
like-
be
That's
gonna be
small,
close to
right?
100. Yeah.
Oh, it's not as fast as
So that's like about half of a hella,
What's that?
Whoa,
half of a hella fast, I think.
Yeah, maybe it's not quite that fast. It's pretty fast though.
Yeah.
Pretty fast, but it's not a hell.
All right, so got that. So what about this one then? Bike rider approaches a hill on a level ground at a speed of 12.9 meters per second. The mass of the bike and rider combined is 98.7 kilograms.
You're supposed to.
The rider coasts up the hill and comes to rest 7.02 meters above the level of the road. So we want to know the bike lost how much energy to friction as it coasted up the hill. Okay, we could do this one now. When he's coasting up the hill, what are the forces acting on the bike? Gravity and friction, right? Okay, and we could, you guys could do this one right now, it'd be fine. I do want to show you one more little thing. I showed this to you the very first day we talked about this, when we did our overview of work and energy, but it's not up here, it didn't need to be. We can define, I don't think it is, no it's not. We can define mechanical energy is equal to the sum of kinetic energy and gravitational potential energy, which we call, I think we call the GPE, really that's U. We call that U. Okay, in the book, and even in this book they call it U, for potential energy. So that is, now U is defined, remember, U is defined as mgh, right? That's the amount of energy we've stored gravitationally by moving an object up a hill, for example.
So what?
Right.
So what is U? What is U mean?
Gravitational potential energy.
Gravitational potential energy. So that's mgh. Now think about this. If I take this object right here, it doesn't matter the path that I take. This is what's interesting about this. Why this is a special. This total quantity is special. If I take this thing and I do some work to move it up and set it on a shelf, doesn't matter the path that I take. If this thing has a mass of 1 kilogram and it starts here and I move it up to a shelf that's 1 meter higher than that, then the amount of work that I've done against gravity is just the vertical displacement times the force that I had to apply, right? And the force that I'm applying is just, assuming I just move this up at constant speed, let's say, just to make it easier. It's just counteracting the weight, right? I'm just offsetting the weight. So that would be 10 newtons roughly, right? Times 1 meter would give me my 10 joules of work that I'm doing against gravity, right? If I set it there, it sits there and the energy is stored, right? If we knock it off the shelf, what's it gonna do? It's gonna fall down. How much kinetic energy do you think it has when it gets to the level of the table? Well, 10. It's got 10. It's got 10 because gravity's giving me back now. Gravity is doing the work on the object that I did to set it on the shelf, right? So you really are storing energy there, right? And that's how a dam works, right? With a dam, all you're doing is taking the gravitational potential energy of the water in the reservoir behind the dam, and when it falls down through the dam, and it's not perfectly efficient, it turns some turbines, and you're harnessing the stored gravitational potential energy of the water, right? You could, if you wanted to store energy, and this has been done before. What do you do if what's the downside of and I'm all for wind and solar, but I mean, what's the only real downside of wind and solar?
Eventually the wind will run out.
No, the wind will never run out. But there is something that is kind of a practical problem with wind and solar.
Can't be doing 24/7,
It's not going 24/7. The wind blows when it blows.
and you're not getting quite as much.
Well, at this point, it's a little more expensive just because the infrastructure isn't there, but that'll change. But one problem is that the sun only shines at certain times, and the wind only blows when it blows, right? And so what do you do if those aren't the times when you need the power, right, in the cities, for example?
Like,
So batteries.
So, well, okay, what you gotta do is you gotta find a way to store that energy, right?
By lifting up pebbles and then having them fall
Well,
down.
one way to do it is, you can pump water up into a reservoir and then just release the water when you need the power. Downside of that is that it's not super efficient, right? I mean, you're gonna lose some, you're always gonna lose something. But that's one way to do it. There are other things that you can store, you can pump, compressible fluid into a big impermeable chamber, like a big cave. And then you can release the gas and turn a turbine when you release the gas. You can store it in a great big flywheel that spins. And then you get the rotational kinetic energy, the flywheel that you can harness with a clutch and gears, when you wanna generate power. You can store it in a battery, yeah.
Could you produce like an unlimited source of energy if you pumped water like through turbines?
Well, no, that'd be perpetual motion machine, which you can't have. Because think about that, the energy, you have to have energy to run the pump.
Yeah.
The pump is less than 100% efficient, so it's a losing battle, right? Because the energy you produce is not enough to pump the water back up to the dam.
Well, no, like if you had a building and you had a bunch of water and you just pumped it like up and then through turbines and then reuse that water.
Well, okay, but
Not
when you
make
pump it through turbines, you're having to provide, what you're implying there is you're having to provide the energy to turn the turbines, right? The turbines are producing energy, but you're not getting as much out as you put in, because it's less than 100% efficient. See what I'm saying? Now, one thing that's like, how does a hybrid car work? While we're on this, kind of a good little subject.
Gravity charges when you go down.
Well, okay, what does a hybrid car do, like a Prius?
It's electrical and
It's electrical and gas, right? But so let's take what are the ones they build in Palo Alto now? The real fancy ones.
Well, my
Teslas, yeah,
mom
Teslas.
has a C-Max, and it charges when she brakes.
Right. Okay. So there's regenerative braking, right? So with these cars, what does the engine do? The engine
So
is an
like you have to
electronic
ride.
motor, is what it is, right? So you're going to take the stored charge
It's
in the batteries,
exactly top-notch.
and you're going to run a current through the motor, which turns the stored electrical energy into kinetic energy, right? When you put on the brakes, instead of what happens in a normal car when you put on the brakes? Heat. Yeah, that's all it is. You're just wasting all that energy, right? You've got the brake pads that clamp down on the rotors, and they stop the car by the friction between those two materials. Well, where's all that heat go? It just gets dissipated into the environment as heat, right? No useful work is done there. But with a hybrid car, that's not what happens. With a hybrid car, it just reverses the direction of the motor. It becomes a rotor. So when you use the kinetic energy of the car to spin the rotor, which resists you, because what you're doing is you're driving magnets against each other, which generates a current, which charges the battery, right? So the braking force is actually an artifact of the process of storing energy. What's that?
So like an engine brake.
It is. It's like an engine brake, only this one really does something. The engine brake, all the engine brake does is it just takes the load off of your brakes. It doesn't really do anything though, right? It's not, other than maybe it charges if you have a crappy battery and it charges a battery for you in your car so you can play the radio or something, right? But this is different. This is actually storing that energy in a form that's usable.
So as it stands now, we don't really have any really efficient batteries, like all the lithium ion, so like not worth it. Do you think that like potential energy batteries, like moving water up and then releasing it when you want the energy, is going to be the future?
No, I think the way it's going to be is batteries. It is going to be batteries.
Large
Yeah,
scale batteries.
it's going to be large scale batteries that just work differently than like a small battery. But it'll be almost exclusively, I'm sure, it'll be batteries.
Well, what's the advantage of a battery over something like a flywheel?
Just more efficient, stores it longer. Yeah.
I feel like soon they're gonna have cars with solar panels on the roof.
I think they already are
They
being
already
implemented.
have
They made a car
one.
full of
Yeah.
solar panels, like, and it worked just on the solar.
Now, don't think that you're not gonna be able to drive along and have the incident light power the car. But
That won't
while
be
the car
enough.
is stopped at an intersection or at a park, it'll
Yeah.
constantly charge the battery like a trickle charger. Yeah. It's Tesla, I think I heard, I might have this wrong, but I thought I heard recently that Tesla now is more valuable than Ford.
Probably.
That it's,
Because
they've
like
invested,
$250,000.
if you, the number of cars isn't nearly as big right now, but they've invested, they just built a state-of-the-art, like they're by far the biggest battery manufacturer in the world. And they just built this state-of-the-art plant in Palo Alto that does nothing but just build these really thin lithium-ion batteries that you mount in the frame of the car. And so if you kind of extrapolate into the future where their company's gonna go, is that our 20?
Yeah.
Gosh, Siri? All right, I said
You
20.
just keep on talking,
No.
you just wanna actually do
We'll
it.
pick it up tomorrow,
I'm
that's
not
fine.
saying-
There's so many
Yeah, me
problems with Ford's electric cars.
Yeah, I know.
Well, and like the biggest one that my mom is facing right now is so we got that car, so